Infinity and Asymptotes Part 2. I'm going to show you now how to find horizontal asymptotes and how to find slant asymptotes, okay, using limits. Method to find horizontal asymptote of a rational function of the form p of x over q of x, where p of x and q of x are polynomials, right? Rational functions. Two steps. First step, compute the limit as x approaches plus or minus infinity of p of x over q over x of x. Now, if the result of this limit is a real number L, then there is a horizontal asymptote with equation y equal L, right? If your limit is 0, y equals 0. If your limit is 3, y equal 3. If your limit is -5, y equal -5 will be the horizontal asymptote. Otherwise, you will say no horizontal asymptote. What is this otherwise? Well, let's say you take the limit and you get the symbol, such as infinity or minus infinity. Then in that case, you say, this function does not have a horizontal asymptote. Example, for example, suppose they say find the horizontal asymptote of this rational function. Okay, well, then we follow this two-step method. First step says take the limit as x approaches plus or minus infinity of this rational function, right? So let's do that. Limit as x approaches plus or minus infinity of this 12x minus 7 over 4x plus 2. Well, we know that we have a technique to do that. We have to identify the highest power on the denominator, in this case is x, right? And next what we do is this. We take the limit as x approaches plus or minus infinity of 12x minus 7 over this guy, x, right? Divided by 4x plus 2 over x. Now we do the algebra here. We simplify as much as we can. Limit as x approaches to plus or minus infinity of x into 12x is just 12, x cancels, right? Minus x into 7 over x into 4x, x cancels, 4 stays, plus x into 2 over x. Now we identify these terms containing x on the denominator or powers of x, right? We know that in the limit, since x is a very positive number, a very negative number, this goes to 0, right? What is left? 12 over 4, which is just 3, right? Now, since this number 3 is a real number, right? This is a real number. This is a real number. It's not a symbol. It's not infinity. It's not negative infinity. It is a real number. Then we have the right to say that we got ourselves our horizontal asymptote. Then there is a horizontal asymptote h dot a dot, shorthand for horizontal asymptote, right? There is a horizontal asymptote having this equation, y equal 3. Y equal 3, right? That's it. All right. Now, suppose they ask you again the same question, right? Find the horizontal asymptote, but between parentheses, they write if it exists of this. Well, if we follow the same method, right? The one that we just follow there, if we take the limit as x approaches plus or minus infinity of this function, 5x to the 4 minus 2x squared minus 7 over x plus 2x cubed. And we identify the largest power of the denominator, which is x cubed, right? And we proceed with our method, right? To figure out if this is going to lead us to a real number or not. Well, this will be 5x to the 4 minus 2x squared minus 7 divided by this guy x cubed over 5x to the 4 minus 2x squared minus, no, it's the denominator here, be careful. Denominator here, x squared, well, not x, x plus 2x cubed over this guy, right, x cubed. This is what we're gonna do. Now, this will be limit as x approaches plus minus infinity of what? This guy into this guy, x cubed into x to the 4 is just x, 5x, minus x cubed into x squared, simplify is just x on the bottom, right? 2 over x, minus 7 over x cubed over x cubed into x, 1 over x squared when simplified, plus x cubed into 2x cubed, x cubed into x cubed 1, this is 2, right? This is what I get. Now, I know that all these guys, the terms containing x on the denominator, they all go to 0, right? 0, 0, 0, because x is big in absolute value. It could be a big, very big positive number or a very negative number. This is 0 anyway. But this is not 0, right? It's 5x. So at that point, you end up with this, right? Limit as x approaches plus minus infinity of 5x over 2. Imagine you plug there plus minus infinity, a very negative number, a very positive number. This number 5 multiplying plus minus infinity is the same as plus minus infinity, right? 2 into plus minus infinity is the same. So this guy plus minus infinity. Now, this is not a real number, right? A real number. So conclusion, then no horizontal asymptote. Then no horizontal asymptote, okay? So only when you get a number, you get a horizontal asymptote. If not, you just say no horizontal asymptote. There will be a choice there that will say that, right? So that's the choice that you have to pick there. All right, guys, very good. So now time for you to practice here on the worksheets. Can you try the first one here? This one? Find the horizontal asymptote there. And for that, you have to take the limit of this function, this rational function, and see if indeed you get a number, right? If you get a number, then you are done. That's the horizontal asymptote, right? If not, you say no horizontal asymptote. And I will give you a little trick here, a shorthand. Aha, Sarah, very good. Sarah, Ruby, Oscar. Very good, guys. Very good. Excellent, right? Yeah, when you do this process, then you realize that as long as mathematicians got this, as long as these 2 degrees are the same, when you do this process, all right, of dividing by the highest power of the denominator, which is x, right? You end up basically dividing the 4 and the 1, right? See, guys, here. So mathematicians figure this out and say, okay, this is 4 minus 9 over x. This is 1 minus 6 over x, but these guys will go always to 0, right? So the dominant will be this guy and this guy, right? 4 and 1. So that's what you keep in the end, right? So then this will be just 4 over 1, 4. Then horizontal asymptote is y equal 4, right? Y equal 4. This is the horizontal asymptote, the equation of the horizontal asymptote. So you gotta go for this, right? So these type of rational functions, the ones having the same degree on the numerator, the same degree on the denominator, mathematicians call them equally balanced. Equally balanced, right here. Equally balanced. Or equally heavy. I think it's better word, equally heavy. Equally heavy. So for equally heavy rational functions, you just look at the first coefficients, they're called the leading coefficients, right? And then you divide them, you get your horizontal asymptote, right? All right. Now, there are other situations where, such as this, for example, well, that will not be the case. So can you try this now? You're supposed to take the limit x squared plus 7x minus 2 over x minus 2, and then see if this is a real number or not. If it is not a real number, then you will say that this doesn't have a horizontal asymptote, right? Remember, this is the largest power of the denominator. Mm-hmm. Yeah, I can see. Yeah, Oscar, very good. Sarah, very good. Excellent, excellent, guys. Very good. Yeah, mathematicians, when they were doing this, they realized that when you have this type of rational function where the degree here is bigger than the degree here, they call them top-heavy functions. So top-heavy, because the biggest degree or exponent is on the numerator, right? Top-heavy. And they realize that for top-heavy rational functions, when you do the math here, you will end up with the following. You will see. X squared plus 7x minus 2 over x here, and x minus 2 over x here, right? Look, if you divide x into x squared, that's going to be just x plus x into 7x, that's going to be a 7 minus 2 over x, right? And here x into x is 1 minus x into 2 over x. These two guys, we know they go to 0, right? 0, 0. This guy doesn't go to 0. This is instead plus minus infinity, right? Plus 7 is a constant over 1. 7 is nothing for plus or minus infinity, so it gets absorbed by plus minus infinity, and plus minus infinity divided by the number 1 is just itself plus minus infinity, right? So we get something that is not a real number, so therefore we have to say no horizontal asymptote. Now, mathematicians realize that for top-heavy rational functions, no horizontal asymptote, then no horizontal asymptote. So if you are getting a top-heavy rational function, no horizontal asymptote. Indeed, they have a different type of asymptote that I will explain to you next. Right, this is equally heavy, top-heavy. We know that it's not top-heavy, it's bottom-heavy. Yeah, for this one's bottom heavy. Yeah, let me see. If you do the math, when you divide by x to the 4, x to the 5th power, right, both, this will lead to 0, this limit. Okay, so if you divide by x to the 5th power, right, which is the highest power of the denominator in this case, right, which is this, right, dividing this into this, 1 over x, 1 over 3x, 4 over x to the 5th, this will be 0. So 0 divided by 3 in the bottom, 0, this limit. So what does it say? That the horizontal asymptote should be y equals 0, right? Should have an equation which should be y equals 0. So for bottom heavy, horizontal asymptote is always y equals 0. All right, so mathematicians kind of organized all this, right? And they came out with this nice shortcut I'm going to show you here, summary, right? They say whenever you have a rational function, there are 3 possible scenarios. either your rational function is top heavy, equally heavy, or bottom heavy, right? Depending on these degrees, these exponents, right? Whatever is the dominant determines if you are dealing with a top heavy, bottom heavy, or equally heavy rational function. Now, if you are dealing with an equally heavy here, how do you know, Professor? Because look, N equal M, equally heavy. Same degree, right, for the numerator and the denominator. Then F has a horizontal asymptote, and the horizontal asymptote will be determined by the division of these two numbers. This turns out to be the dominant. You can ignore the rest, right? These two are dominant. So your horizontal asymptote will be just this, the division of the two leading terms. That's for the first scenario. Second scenario, what if your rational function is bottom heavy? What if this guy N is less than M? What if M is the dominant now? Well, for bottom heavy, we said that we will end up with this situation, right? Y equals 0, because this will dominate. So the horizontal asymptote will be Y equals 0. So maybe we can highlight here. Yeah. The third scenario is this. What if your function is top heavy? If the degree of the numerator is greater than the degree of the denominator and greater than M, then you have to be careful there, because this is not going to show a horizontal asymptote, right? We know that. But it will show, for some particular cases, what mathematicians call a slant asymptote, okay? A slant asymptote, also known as an oblique asymptote, okay? A slant asymptote, oblique asymptote. What is that? Well, guys, notice that so far we have horizontal asymptote, vertical asymptotes, right? But what if they ask you to figure out an slant? What is an slant asymptote? We give us an example. Sure, I can give you an example of a slant asymptote. Let me make up something for you. Yeah, this one, for example. For you to have an idea of what it is. Y equal 1 plus X over X. Yeah, so this, let's make it a square. That's it. You see this, guys, in there? This is the graph of this guy, and the slant asymptote is this. I will show you how to get it. This blue asymptote, this is a slant asymptote. Is not horizontal, is not vertical, right? Neither horizontal nor vertical. Is instead an oblique line. And the curve you can see, right, is getting closer and closer to it in this direction, getting closer and closer to it in this direction as well. Right? It's just called slant asymptotes, or also called oblique asymptotes. All right, so this is what corresponds to the situation when you have a top-heavy rational function. But we will be able to find this slant asymptote when this exponent, the degree of the numerator, is one more than the degree of the denominator, okay? And we will do it via division of polynomials, as is stated here, right? So I will show you how this works. For example, suppose they give you this top-heavy rational function and they ask you to find the slant asymptote and then they sketch the graph of this function. So how you find the slant asymptote? Well, you do it by division, right? As is stated here. You have to divide these two polynomials. Right, let's do the division of the two polynomials. And after that, we will identify our slant asymptote with this part, with the quotient, okay? Maybe we should highlight it. The quotient of this, ignoring the remainder, should give you the slant asymptote. You will see. So step one, right? let's do the division of these two polynomials. In order to divide these two polynomials, I better complete these polynomials. This is 3x squared plus 4x, doesn't have the constant term. Remember, in pre-calculus, we learned that whenever the polynomial is not complete, we complete it, especially if you are dealing with the dividend, right? Divisor doesn't have to be completed. But then you go ahead and do this division. 3x squared plus 4x plus 0 divided by x plus 2. And this can be done also using synthetic division. Then I will show you some alternative. Whenever the denominator is of this form, x plus 2. All right, so I start with this, divide this by this. That is 3x, right? The 3x here. 3x multiplying this whole thing. 3x multiplying this whole thing is what? 3x squared plus 6x, right? Write it down here, 3x squared plus 6x. And what you have to do next is you have to subtract, right? To subtract, I help myself by distributing the sign. This will make this positive 3x squared, negative 3x squared, negative and positive negative 6x. This will be 0, 4x minus 6x minus twice x, minus twice x. Bring down the next digit, which is a 0, repeat the same process. So we do this one more time. Okay, negative 2x divided by x now is negative 2. It's right here, negative 2 on top of the constant term. Negative 2 multiplying x plus 2 is negative 2x minus 4. Negative 2x minus 4. Now you gotta subtract this from this. To help myself, I distribute the multiplication by this negative sign, negative and negative positive, positive 2x here, negative and negative positive, positive 4x. Negative 2x plus 2x 0, 0 plus 4, 4. This is the remainder, right? The remainder. So the function f of x then can be written as follows. F of x equal quotient 3x minus 2 plus remainder, this 4, over divisor x plus 2, right? But notice, guys, this guy goes to 0 for big values of x, right? For big, in quotations, values of x. So basically, this is what you have to consider to be your slant asymptote, because the function will get closer and closer to this linear function since this goes to 0, right? For big values of x. So then this should be, yeah, well, it's right here in the limit, right? For big values of x in the limit. So to put it simple, you pick this up and you say, then a slant asymptote is y equal this guy, 3x minus 2. What you get from this division of polynomials, right? Very good. Now, sometimes students ask me, is there an alternative to avoid this long division? Yes, there is an alternative. It's called synthetic division, right? Using synthetic division, which is something that you might have seen in pre-calculus, right? If you just work with the coefficients and you write 3, 4, and 0 here, and on this corner, you write the opposite of this guy, the opposite of the 2. It's called synthetic division. Negative 2, you can do this. 3 comes down as it is. 3 times 2, negative 6. The sum of these two is negative 2. Negative 2 times negative 2, 4. 4 plus 0, 0. 4 plus 0, sorry, 4. Separate the last one, that's the remainder. And from here, you get your divisor. 3x plus minus 2 is just -2, right? And the remainder is this. The remainder is 4, right? This is what I got here, right? So you can use this too. Yeah, but we found then our slant asymptote, right? That was part A. They say now graph this rational function, right? Figure out the graph. So it's part B. So for part B, we're gonna graph this. All right, so sketch the graph of it. To sketch the graph, guys, I would say quickly graph the slant asymptote, right? And the vertical asymptote that comes from here. Let's use a different color. Look, from here, vertical asymptote, x equal -2, right? Because it comes from setting this equal to 0. X equal -2 is the vertical asymptote. We have the slant asymptote 3x -2, right? So let's graph this too. All right, so then basically you're gonna have something like this. Yeah, let's say the x equal -2 was the vertical asymptote, right? X equal -2. So here, this is your vertical asymptote, right? X equal -2 vertical asymptote. Now, the oblique asymptote is showing a slope 3, y-intercept -2, right? So let's say 1, 2, y-intercept -2 here. And a slope 3 means run has to be 1, the right has to be 3, right? So here, more or less this line, right? Yeah. Yeah, very good. So now, when you have this line, if you extend it, perhaps you're going to get something like this. Figure out with the scale. So, yeah. Very good. So now you just have to graph your function there, right? Yeah, let's create more space here. So, very good. So now, in order to graph this, use test points, right? We know that the curve could be asymptotic here and here, perhaps, right? Because asymptotic to this slant asymptote, asymptotic to this vertical asymptote, or perhaps could be asymptotic here, asymptotic here, asymptotic here, asymptotic here, right? In order to know which curves you have to take, just like we did before, use some test points. For example, if you look at the test point 0, right? 0. This is the slant asymptote. Now let's just make this continuous line here for you to not to get confused. This is not part of the graph, it's just the asymptote, right? Yeah, so now use test points. If you evaluate 0 at the original function, 0, right, at the rational function 0, what do you get? The original function at 0, this function at 0 is 0 here, 0 here, 0 plus 2, 2, 2 into 0, 0, right? 0. So our function f of x evaluated at 0 is 0. What is that telling me? It's telling me that this point is a point that is part of the graph. So this tells me that definitely this guy, the curve has to go like this. All right, like this. Asymptotic here, asymptotic here. So there we have that. Now, next, We'll make it nicer. Next. Yeah, cannot be like this, right? It has to be like this to catch this point. Yes, 0,0. Has to go to this point. Now, another test point could be, for example, you could take, since we know that this is -2 here, right? -2 there, where the vertical asymptote is, something on the left could be -3, for example, test point, to see if where do you land, if here or here, right? So f evaluated at -3. What is that? Well, you take your original function and you substitute there -3, right? So let's do it here in the calculator. So 3 times -3 is squared plus 4 times -3 all over -3 plus 2. Plus 2, right? I get -15, right? So -3 should go with -15. So it's somewhere down here, right? So it tells me that this point will have an output value somewhere here. So therefore, the curve over here should go like this, right? Something like that. Now, how high, how low, don't worry about these points, guys. It's just a sketch. So if you want to find this, you will have to use derivatives and stuff, but let's don't complicate things, right? Just leave it like this. And this should be enough for you to identify this among the choices. This was -15. Okay, this point. So I'm going to write here this associated with -15. Yeah, and that's how you use your slant asymptote in order to figure out the graph. Here is another example. I think this is a little bit simpler, but let's do it together so we can, you will have an idea again how this works, right? Yeah. Find the slant asymptote. Again, we have to use, you have to complete the polynomial here. Doesn't have x term, doesn't have constant term, and then we have to do the long division, right? Long division here, x squared plus 0x plus 0 divided by x minus 1. If you divide these two, x squared divided by x is just x. X times x minus 1, x squared minus x, that goes here, x squared minus x. Subtracting this, I help myself distributing the sign this way, plus x. 0 here, 0 plus x is x. Bring down the 0. Repeat the process. X divided by x is 1. 1 times x minus 1 is just x minus 1, right? That goes here. Subtracting this, you're going to get just 1 as a remainder, right? Yeah, because this guy becomes minus x minus x0 plus 1. So this subtraction 1. Now, bottom line, your function, the one that you have here, is equal to quotient, which is this x plus 1, which we are interested in, right? Plus a remainder divided by this device, right? We ignore this because for big values of x, this is 0. We keep this. So this is your slant asymptote. Yeah, your slant asymptote is that, so that then slant asymptote y equal x plus 1, right? But also we have that the vertical asymptote from here, vertical asymptote is just x equal 1 once you set this equal to 0, right? So vertical asymptote x equal 1. Once you set x minus y equal to 0, this is what you get for vertical asymptote. Vertical asymptote x equal 1, slant asymptote x plus 1. you set that on your XY coordinate system, and this should help you to graph, right? Just as this. Yeah, so again, the vertical asymptote is x equal 1. So now on the right, let's say 1 is here. Let's move it a little bit to the right. Yeah, so let's say your vertical asymptote now is this. X equal 1, vertical asymptote, slant asymptote, y equal slope 1 plus y-intercept 1. So it's this, right? And then using test points, you can figure out the two curves associated to this, right? Yeah. All right. So now, using a test point, I know that this is the number 1, so I can use test point 2, for example, and see where the output value lands. So f evaluate at 2 is equal to what? Let's use our calculator, and this is the function, right? So at 2 squared over 2 minus 1, it's just 1, it's just 4, right? 4. So the partner of 2 is 4. Up here, right? 1, 2, 3, 4, up here. Notice, right? Up there. So it's here. So which is telling me that the curve should be this one, right? Going through that point. Asymptotic here to the slant asymptote, asymptotic here to the vertical asymptote. Now, for this part, we can use another test point, for example, 0, right? Very convenient test point. So at 0, notice that this function, evaluate at 0, this will be 0 squared 0, 0 minus 1, 0 divided by minus 1, 0. 0 goes with 0, so we're talking about this point now. So therefore, the other curve should be asymptotic here, passing through this guy, and then asymptotic here, right? So these two. Yeah, f of 2 was 4, right? So 4 here. F of 0 was 0. So our test points, and then you get the two curves. Okay, guys. So now, how this is on the worksheets, at least let me show you one example. This is to find the slant asymptote via division. You take just a quotient, that's the slant asymptote. So this shouldn't be a problem, but maybe we should try this one, right? Try to figure out, for example, the graph of this or this. Let me see. This is one problem there. Let's do this one. This is reasonable. Can you figure out the graph of this function? I will give you the hint. This is minus x squared minus 2x plus 2 written in an organized way. And then dividing each of these. We don't need to do long division because the divisor is very simple. This is minus x minus 2 plus 2 over x. Remember, the remainder goes to 0 in the limit, right? So this is going to be your slant asymptote. Slant asymptote. So slant asymptote. Y equal minus x minus 2. Vertical asymptote. Vertical asymptote. Set the denominator equal to 0, x equal to 0. So vertical asymptote is just x equals 0. So try to figure out the graph of this and choose which of these 4 graphs is the one, right? So let's try to graph this. Yeah, maybe I should insert here. Yeah. one vertical asymptote is x equals 0. So x equals 0 is this guy, right? This is the vertical asymptote. X equals 0. The slant asymptote is this, right? Slant asymptote, slope -1, y-intercept -2. So let's say 1, -2 is here. Since the slant, well, the slant asymptote has this slope -1, invisible 1 there, it's gonna go like this, right? Yeah, but now the trick is, if this is the slant asymptote, which curve we have to take, which curves, this and this, or perhaps this and this. Use test points and figure that out. This is slant asymptote, vertical asymptote, right? The slant asymptote has this equation, minus x minus 2. Yeah, so we gotta figure out now which of these 4 should be the graph of that. And for that, let's use test points, okay? Test points. First test point that I'm gonna use is -1, perhaps would be a good test point, right? -1. Yeah, -1, I think would be a good test point, yeah, because it's here and I will get to know. So evaluate your function at -1. What do you get? Your original function evaluated at -1 will be this, 2 minus 2, -1 here, minus -1 squared over -1, right? This is positive 2, 4, minus 1, 3, minus 3, right? F at -1 minus 3. Very good. Now, this minus 3 is showing that this -1 should be paired up with something here on the bottom, 1, 2, 3 here, right? -3. So I'm talking about a point down here, right? Right? So this is telling me that the curve then should go this way, right? Asymptotic here, somehow passing through this, and asymptotic here, right? Different than the previous cases. This. And over here, I can take as a test point 1. What is F evaluated 1? 2 minus 2 times 1 minus 1 is squared over 1. 2 minus 2, 0, minus 1 here, minus 1 here is just minus 1, right? So minus 1 is here. So these guys are paired up here. Minus 1 is paired up with 1, which is telling me that now the curve that I have to consider is this, right? This asymptotic here vertically and asymptotic here to this slant asymptote. So these two. So therefore, guys, the one that we have to choose is this. So here, asymptotic here, asymptotic here, asymptotic here, asymptotic here. This one should be this. And they tell you the asymptotes looks here too. Asymptote, vertical asymptote, x equals 0. Slant asymptote minus x minus 2, as we got here, right? Minus x minus 2. Okay, guys, I think we have to stop with this. Don't worry too much about technicalities here, because remember, there is no homework associated to these sections, right? Just try to see how you can organize your methods, your knowledge, such that in a simple way you can get this shape, right? I show you how easy with the test points you can get a sense of where the curves are, right? Sometimes they are here and here, but some other times they are here and here, right? Use test points, it should help you. And of course, you have to find the slant asymptote via division of polynomials and the vertical asymptote by setting your denominator equal to 0, right? All right. So